Hey, welcome back, guys. Class is really getting small now. All right. Just a quick note. I uploaded an announcement. I don't know, I'm getting some kind of crazy reflection off my camera. Okay, I uploaded a file, a PowerPoint presentation, which has a list of about, I don't know, 8 or 9 examples of different types of chemical reactions. So they're actually real examples. So you can see the scientists there, the chemists demonstrating a particular reaction. Some of them are pretty dramatic to give you an idea of the reaction that proceeds. So download it because it's pretty big and they won't let you really view it on the web. So feel free to download it and then take a look at it, and it will help you with the types of reactions that we just talked about. Also, I wrote in there the actual balanced chemical reaction or the reaction they're talking about. Okay, so another resource for you. All right, so that brings us into this new concept called the mole. And sometimes the concept of the mole can be somewhat confusing. And it's understandable. It's a new concept. It's a crazy word called the mole. But what I want to do is to actually show you an alternative example of this concept. Like an alternative example, which you're well aware of what it is, because I'm sure you used it someplace somewhere. And that is the concept of a dozen. Okay. Now, specifically, I'm going to talk about eggs right now, because why? We're all familiar with that, right? And first, point number one, we all know that in 1 dozen, there is a value associated with that, and that is 12 units of something. It could be anything, 12 units, 12 units, 12 bananas, 12 pack, 12 beers, anything, okay? It's simply a number. The description is the dozen, the value associated with the dozen is 12. Now, we have the mole, which is nothing more than a description of a number. In this case, it is a very large number. And it's going to bring you back to scientific notation, because we're going to have to refresh your memory on how to use scientific notation on your calculator, okay? And so 1 mole is a large number. It's specifically 6.02 times 10 to the 23rd. And I emphasize here unit, just like 1 dozen is equal to 12 units, okay? It just happens to be a humongous number. Take that decimal point, and I give you some examples to give you some perspective as to how big this number is. Take that decimal point, move it over to the right 23 times. That gives you an idea how big that number is. All right, so let's talk about the concept of a dozen, and then we're going to take that concept and extrapolate it into the mole and how that relates to the elements and everything else that we're going to eventually be working with. Because when we need to determine quantities like grams of reactants or how much product we make, we cannot calculate on a gram to gram basis. We have to have a unit that is respective of each particular compound. So we talk about the mole. I cannot talk about going from apples to oranges unless I have a common unit, a common factor between the apples and the oranges, which in that example would be fruit. When we talk about chemical reactions, I cannot talk about compound A, compound B with respect to can I relate each other unless I convert them into moles, okay? Moles is very crucial when we start doing calculations. So more on that in a bit. But let's talk about eggs for a second, because we're all familiar with that. Okay, we know they're small, medium, large. Okay, so we have one small. Let me rewrite that. One dozen small. Oh. Okay, small, which of course, let's say for argument's sake that they weigh 100 grams, that one dozen weighs 100 grams, okay? And that equates to 12, does it not? Because we talk about one dozen. All right, so let's talk about one dozen medium, okay? Well, for argument's sake, let's just double that weight and we call that one dozen medium eggs weigh a total of 200 grams. And guess what? I still have 12, right? It's a dozen. And then the last one, we can say one dozen large, and we'll say, okay, 300 grams for that one dozen large. And guess what? We still have 12 eggs, right? Now, obviously, as you go small, medium, large, the size gets bigger, and therefore the weight gets larger, much like the atoms. When we talk about hydrogen being the small atom, it only has a weight of 1.01, okay? And we go all the way to, say, gold, it's 196, I believe. I'll look it up here in a second, grams per mole, okay? Now, with this in mind, if I asked you, if I have 24 small eggs, how much is the weight for 24 small eggs? Could you calculate that given the information I gave you up there? What do you think? Well, let's think about that. If 12 weigh 100 grams, stands to reason that twice that will weigh 200 grams, right? Of course. And of course, if I had, and another way to say that is if I have, let's say I had 3 dozen of the eggs, what would be its weight of small? Got 3 dozen small eggs. How much do they weigh based on the data you got there? Anybody want to give a shot? If 1 dozen weighs 100 grams, doesn't it stand to reason that 3 dozen will be 3 times that, 300 grams? Sure. Okay. I could have said, I said 3 dozen, but I could have easily have said 36 eggs, right? Because I know that if there's 36 eggs, that's 3 dozen, and each dozen weighs 100 grams. Boom, I know the total weight. So I could have gone the opposite direction and say, all right, 300 grams of small eggs. How many dozen would that correspond to? Okay. You see how I can work the problem given this information that in 1 dozen weighs 100 grams and there's 12 in 1 dozen. Okay. So if 300 grams of small eggs tells me that I must have 3 dozen. Because I know that every 100 grams of small eggs is 1 dozen. And if I have 3 times that, then I must have 3 dozen. And I can do the same for medium and large and so forth. Okay. So now the other aspect too here is this. Let me clear all this up. 1 dozen small, I'm just going to go small, equals 100 grams. Guess what? That is a ratio. Remember when we were doing conversion factors? We had 1 inch is equal to 2.54 centimeters. and I can write that ratio either with centimeters on top or centimeters on the bottom. I can do the same thing here. I could say that 100 grams of small over 1 dozen. Okay, that's my ratio. Or I can put dozen on top over 100 grams. Okay, and so if I ask the question, if I have 5 dozen, how many grams does that correspond to? Well, I set up my problem like we did the conversion factor. I set up 5 dozen, okay, for the small eggs. That means I know that a dozen has to be in the numerator, right? And grams must be in the numerator, and dozen must be in the denominator. Why? Because I want dozen to cancel. So I'm going to use the one on the left. So 100 grams go on top, 1 dozen goes on the bottom. Okay. And so for 5 dozen eggs, it would weigh 500 grams. Okay. Now this ratio business here, we can do that for any ratio that we have. Now let me send you to the periodic table for a second. Let me clear this up. Because on the periodic table, you have an atomic weight for every element there. Okay. And let's take carbon, for example. I'll show you that. It's carbon, number 6, and then in the bottom it says 12.01. It's numbers and they have no units. And here I'm here to tell you, the atomic weight, which is the number below the symbol, has units. Specifically, the units are grams per mole. Okay, just like the dozen eggs had the small eggs, it said 100 grams per dozen. That was our unit factor. Remember that? How I set that up? Or the medium eggs, 200 grams per dozen. Okay, 200 grams per dozen. And the large eggs was set up at 300 grams per dozen. Now, these 3 moieties here, what do they all have in common? They have a common dozen, which means there are 12. Okay. Every element has an atomic weight with those units. Okay. Grams per mole. What that means that what they all have in common, quantity-wise, is 1 mole, which is 6.02 times 10 to the 23rd. Here they have in common a dozen, which is 12. Okay. So what does this ratio tell you? That I can set it up 2 ways. 12.0 grams per 1 mole, or invert it, 1 mole, and we're talking about carbon here, 12.01 grams. Okay, carbon, mole of carbon, grams of carbon, mole of carbon. And I'll be using these conversion factors, these ratios, depending on the question asked. Just like we did earlier, I keep track of my units, okay? Keep track of my units to help me set that problem up. Eventually, we're going to be able to do problems where we're going to be setting up at least 3 conversion factors. Okay? Just like we did in the conversion factors when the units, when we're talking about English to metric. Here, we're going to be talking about going from grams of compound A to grams of compound B. Okay, and we're going to have conversion factors here. The common factor for all the elements is moles. Moles, just like the common factor down for dozen for the eggs was a dozen, right? A dozen. Okay, let's go back to the concept of the mole. All right, here's a picture of a scientist that named it after. Kind of interesting looking character. Avogadro, okay? Now, Avogadro's number is denoted by the letter capital A subscript, it's capital N subscript A, Avogadro's number. It is nothing but a number, okay? And it just happens to be a humongous number. 6.02 times 10 to the 23rd. Just like in a dozen is 12. In 1 mole, it's that humongous number. Okay. Now, how big is that number? Well, it's pretty hefty. Okay, here's an idea. 6.02 times 10 to the 23rd, if you write it longhand, equates to 602.6 trillion, which is right here. Okay. Give me 1 second, please. Okay, I'm back, sorry. And so that number, look how big it is. Now, to give you an idea, even a further idea as to kind of put in perspective as to the size of this number, magnitude, I should say, is that if you were counting, say, 1 number per second, that is your rate. So you sit there, you go 1, 2, 3, 4, 5, 6, 7, or 1001, 1002, 1003, etc. By the time you get to the end of that number, it's going to take you 19 quadrillion years to get the end of the number. So you'll be kind of old by the time you're done. That's how large that number is. It's humongous. It's right here. And here's some other units that if you're interested, that sit here. You got a gogoplex, humongous, or Google, which has 100 zeros and so on and so forth. So those are real prefixes, by the way. Big numbers. All right, so that gives you an idea how big that number is. All right, so, and a further example was if you had 1 mole of softballs, and you know the size of softballs, approximately, I don't know, 4 or 5 inches in diameter, ballpark. If you had 1 mole of softballs, all of them together be about the size of the Earth. That's how many you would have. Now, the mass in mole of atoms is equal to the atomic mass in the periodic table. Let's refer it to the periodic table. Now, we have carbon, for example, number 6. Okay, its atomic mass is 12.01. Its units are grams per mole. 12.01 grams per mole for carbon. 12.01 grams per mole. Okay, just like the small eggs would be 100 grams per dozen. So if I had a dozen, it would weigh 100 grams. If I had 2 dozen, it would weigh 200 grams. 3 dozen, 300 grams, etc. Here, if I have 24.02 grams, I got 2 moles. Okay, because each mole weighs 12.01, right? And if I have what, roughly 36 grams, I have 3 moles. So on and so forth. Helium has an atomic mass of 4 grams per mole. 8 grams will give me 2 moles. Okay, and 12 grams will give me 3 moles, etc. The number underneath the atomic weight represents the average weight of the mass numbers of all the isotopes. That's why I get a decimal here, 12.01. Because we went through that scenario where carbon, for example, is carbon 11, 12, 13, and 14, all even numbers, whole numbers. And depending on the percentage of concentration, abundancy on Earth, they will contribute more. And therefore, that's why we can determine that for carbon, carbon 12 is the most abundant isotope because it has a larger percentage overall. That number is closer to 12, 12.01. Okay. And so one should be able to, if someone asks you the question, all right, let's ask the question. If you have 1 mole of nickel, which I've highlighted, circled to number 28, I have 1 mole of nickel. How much does that weigh? How much does that nickel weigh if I have 1 mole of nickel? Anybody want to take a shot at that? The number is right underneath the symbol. What do you see there? 58.69 grams. Okay. 1 mole of nickel would be 58.69 grams. Compared to 1 mole of carbon, which is 12.01. Well, carbon represents the small eggs, right? It's 100 grams per mole. Nickel could represent, say, the medium eggs, right? Where the medium eggs are 200 grams per mole. Well, obviously, it's going to be greater, 58. Why? More protons, more neutrons, okay? And then gold, which is right here, 1 mole of gold would weigh 196.97 grams, okay? Now, and that could represent the large eggs at 300 grams per dozen. Here, 196.97 grams per 1 mole. What all three have in common here is they all have 1 mole. Okay, exactly 1 mole. And that means that they have 6.02 times 10 to the 23rd atoms, all of them at 1 mole. Just like the small eggs that were 100 grams per dozen, there's 12 eggs there. It's a dozen. The medium eggs were 200 grams per dozen, 12 eggs. The large were 300 grams per dozen. Again, 12 eggs. All three, small, medium, large, though they all weigh differently, they all had the same number, the same magnitude, and that was a dozen eggs. Okay, so all of these will weigh differently for 1 mole, but they all have the same number of atoms. All right. Any questions so far? And so, like we said, a dozen is just a number. A dozen eggs, a dozen bananas, a dozen computers, a dozen students. It doesn't make a difference. It's just a number of some entity. Okay, it is just a entity of some sort. It just in chemistry we talk about a dozen atoms. The entity is atoms, or we could be talking about ions, or for that matter, molecules or formula units, like, the whole formula. One mole of sodium chloride, 1 mole of aluminum oxide, things of that nature, okay? And just remember that is simply a number, the mole is. All right, so if you ever ask the question, how many grams in 1 mole of, and there's some arbitrary element, you just go to the periodic table. Carbon, we know that carbon has a mass, a molar mass of 12.01 grams per mole. Okay, so in 1 mole, it will weigh 12.01 grams. Gold will weigh 196.97 grams per 1 mole. Okay, and sodium will have 22.99 grams per mole. What they all have in common is the quantity of atoms of each. 1 mole meaning that they have 6.02 times 10 to the 23rd atoms. All of them will have that. Okay, just like the example of small, medium, and large eggs, a dozen, 100 grams per dozen, 200 grams per dozen, 300 grams per dozen. They all weigh differently. They all have the same number. 12. The mole happens to be also called the chemist's dozen. It just happens to be a pretty big number. All right. Before we can start up with any type of calculations, we have to determine or calculate what is the molar mass, and that is nothing complicated here, really. Simply as this: you got the formula, you determine how many atoms of each are in the formula. You multiply that by their respective atomic weight, you sum all that up, and that is the molar mass of the molecule, okay? And that's why way back when we had pictures of formula structures, we asked you, well, how many atoms here, how many atoms are there? We weren't ready to do any calculations. We wanted you to be able to look at a formula and determine how many atoms of each are involved in the whole compound formula. And so here they're asking you the question is calculate the molar mass of a barium hydroxide. Well, what we need to do first is to write the formula, okay? We have to write the formula, and this is no different from what we've been doing to date. We break everything down to the ions. We know that barium is in group 2A, and when it becomes ionic, it will lose 2 electrons and it has a +2 charge. We know hydroxide. Hopefully you don't know it by now. It should become very familiar because we used it quite often already. Also, that it indicates that that is a base, hydroxide. Remember that. And you can go to the polyatomic ion table and it will give you the formula and the charge for that polyatomic ion. And it's a -1 charge for this unit OH. Remember, we're going to keep them together as a unit. To put these down together to write a formula, we need to add enough of cations and anions to cancel each other out. So we need 2 hydroxides for every barium ion. Hence, our formula becomes Ba. We use parentheses because remember, we want to keep these polyatomic ions together as a unit, okay? And so our formula is Ba parentheses OH and parentheses subscript 2. Now, the next step is we identify how many of each atoms we have in this compound. So we got 1 barium, and we go to the periodic table and we look up the 137. We look up the atomic weight, 137 and change. I'll let you look that up. I'll show you that in a second. We have 2 oxygens, which are total, each one 16 even. So this is 32. And remember, these are grams per mole, unit-wise. And then we have 2 hydrogens, which each one is at 1.01. So we got 2.01. We tally all that up. And once we do that, that gives us what is called as the molar mass, okay? So there's a formula like we just did. And then we tally it up. We got 137.33 units or grams per mole. Okay. For the barium, the oxygen each has an atomic mass, atomic weight of 16. There's 2 of them here. All right. So that is also grams per mole. And then we have 2 hydrogens, each one at 1.01 grams per mole. And so we do the math and we end up with the molar mass for a barium hydroxide is 171.35 grams per mole. Note the ratio, grams per mole, which means that when we set these up for problems, we can write it with grams in the numerator, or we can write it with grams in the denominator. This is for barium hydroxide, okay? Every compound we generate, they're all gonna have their own different molar mass. Depends on the atoms and how many are in there. But this unit here, if we're ever asked, if you have, let's say 20 moles of barium hydroxide, the question would be, well, how many grams of barium hydroxide do I have? Okay, so we're given moles, we want grams, so moles are going to have to be in the denominator. So we're going to multiply this 10 moles by this first factor. Okay, so 10 moles of barium hydroxide divided by the first factor, because that's 171.35 grams over 1 mole barium hydroxide. Guess what? Look at my moles cancel. I got units of grams left. Bam, I'm at my answer, okay? Just like we did with respect to the conversion factor of the English and metric units. All right, that is calculating the molar mass of the compound. So to rehash there, make sure you write the proper formula, okay? Because without the proper formula, obviously your molar mass will be off. And once you get the proper formula, tally up all of the protons and involved in that formula, and that gives you the molar mass. And don't forget the units are grams per mole, okay? Avogadro's number also is a ratio, okay? It can be written as follows, to the left or to the right, 6.02 times 10 to the 23rd, atoms, molecules, ions, whatever you're counting per mole. Okay, so I can write it with the Avogadro's number on top and moles in the denominator, or vice versa. Which one I use depends on the question. Now, to refresh your memory on your calculator with respect to scientific notation, remember we talked about it at length. You have two buttons. You want one of three buttons, I should say. You have a double E button, okay? Or you may have a EXP button, or you may have the newest calculators have a button where you got like the X and to the X, not the button that says 10 to the X, not that button, okay, not that one. There's going to be like a little X in front, okay? So one of these three buttons will actually help you input your scientific notation. You may want to go back and refresh your memory on that, okay? Because you will be using it in this particular chapter to solve the problems. A lot of times the buttons are the primary button, they're up front. If not, check, maybe they could be the secondary, which means you got to hit the second button to access it, okay? All right. So this could be written one or two ways, the ratio that is. And so the question is asked, how many calcium atoms, okay? How many calcium atoms are in 0.025 moles of calcium, okay? So as we normally would do, I would write down what I'm given, 0.250 moles. And notice something about that number, okay? 0.25, I should say. It's about a quarter, right? A quarter is a 0.25. All right, so I'm gonna have a quarter of, I'm anticipating the type of number I'm gonna get, but since I'm starting with 0.25, which is a quarter, I should end up with about a quarter of the value for Avogadro's number. All right, so I'm gonna need a conversion factor here, okay? And I'm looking for units of atoms based on the question. I'm given moles, so that means that I need to put moles in the bottom denominator and atoms on the numerator because I want moles to cancel. Therefore, I will be using the factor on the left, 6.02 times 10 to the 23rd over 1 mole. My units cancel. I have the units I'm looking for. It's a matter of you plugging your numbers in your calculator, and you should end up with roughly a quarter of Avogadro's number, which is 1.51 times 10 to the 23rd calcium atoms. Okay. That's still a lot of atoms. You've got a quarter mole. Okay. Notice something when we were talking about atomic weights, in molar mass, the units were grams per mole. Hopefully you recognize here that you're going to be able to go from moles to grams and vice versa, using the molar mass / atomic weights to get from one point to the other. So if I have moles given, I'm going to use this one here because my moles cancel to give me grams. If I have grams given, obviously I'm going to use the one on the right because my grams cancel and I'm looking for moles. See how that works? All right, next one. Here, they're asking to calculate the moles of 3.75 times 10 to the 27 molecules of oxygen gas. Okay, and so write down what we're given: 3.75 times 10 to the 27 molecules of oxygen gas. Obviously, I'm going to use a factor. I'm looking for moles of oxygen gas. Avogadro's number is going to be written so that I got 6.02 in the denominator. Molecules for 1 mole. 1 mole per 6.02 times 10 to the 23rd. Notice my moles cancel, molecules, I should say, cancel. Leaving me with moles about 2 is what I'm looking for. So you plug those numbers in the calculator, and you should end up with 6,230 moles of oxygen. Okay, quite a bit of moles. All right, Alan, here's some food for thought. Working with moles. Let's take the formula H2O, okay? And how do we calculate the molar mass for H2O? What do we do? We got the formula. Who can tell me the molar mass for H2O? Or at least tell me what I need to do so I can write it in the book, write it here. Any ideas? Remember how we did the molar mass for barium hydroxide? Yeah, we first wrote the formula, that's correct, but then what do we do after that?
Didn't we have to add the atomic mass of both molecules that are in, or both atoms that are in the molecule?
Well, both, but 3 of them. First, have to identify how many of each we have, right? Don't we have 2 hydrogens and 2 oxygens?
Yeah.
Okay. Yeah. So we got 1 oxygen and we have 2 hydrogens. Okay. So now we get the atomic weight for the oxygens, and that's 16.00 grams per mole. Okay. The hydrogens, there's 2 of them, and each one is 1.01. So we have 2.02 grams per mole for the hydrogens, coming from hydrogens. So that gives us 18.02 grams per mole. Okay. So that means if you go out and you had to balance it with you right now, and you weighed out exactly 18.02 grams, you have 1 mole of water molecules, okay? Which represents how many water molecules is that? Okay, what is 1 mole equal to? And I can write this 1 or 2 ways to help you out. 18.02 grams per 1 mole is the same thing as writing as, and we're talking about water here, okay? 18.02 grams per 6.02 times 10 to the 23rd molecules of water. Okay. You know, remember the dozen small eggs, they weighed 100 grams per dozen, which is the same thing as 100 grams per 12 eggs, right? Same scenario. And I demonstrated hopefully how large this number is for only 18 grams. 18 grams is nothing. It's about 100 cc's of water, 18 cc's of water, ballpark, 18 milliliters. It's a small amount, small quantity, okay? But in that small quantity, there are 6.02 times 10 to the 23rd molecules of water. Now, think about how much water is in your body. I don't have any idea. It's quite a bit, okay? And so if I had 36 grams, I double that number, right? And if I have 4 times, I quadruple that Avogadro's number. So imagine all the water in your body and calculate that and determine how many molecules of water you have just in your body. And then take that and extrapolate it with, okay, I got a swimming pool at home. I don't know how many gallons, 10,000 gallons, whatever you've got, big pool, small pool. Calculate how many water molecules in that thing. And then take that number and that calculation and figure out all the water in the ocean, which has, again, who knows? But imagine if with that number, the magnitude is just mind-boggling as to how many water molecules are out here just on the earth. It's humongous, and it gives you an idea as to how small these molecules are. 18 grams, not a large quantity, has a very large quantity of molecules. So these atoms are extremely, extremely tiny. And when they come together, these molecules are just as small. All right, so at this point, we've been calculating, we calculated the molar mass, okay, to give us an idea. We know based on the atomic weight of the elements, how many atomic weight is grams per mole. We took now the elements, put them together to write molecules or compounds like barium hydroxide. That gives us the molar mass, okay? And now we incorporated using Avogadro's number to calculate in a mole how many actual atoms we have, okay? And we went through, oh, I forgot this one. Yeah, this one here, 6,230. So now we're going to use the atomic weight / molar mass to calculate going from grams to moles, okay? We're going to grams to moles. And remember that the molar mass has the units of grams per mole, which we can write as moles per gram. And which one we utilize depends on what we're looking for, what we're trying to calculate, okay? We're using that dimensional analysis that we talked about way back in the beginning with respect to conversion factors, and call it dimensional analysis, call it whatever you want. I just call it, like I stated before, keep track of your units, okay? Follow the units. So the question here says, all right, 2 things we've got to remember here. Well, one thing to begin with is converting what we're given in words to formulas, okay? Notice here, they're talking about oxygen gas. They didn't say oxygen, an atom of oxygen. They said oxygen gas. And we know that there are 12 elements out there that are a gas material. But we also know that a majority of those are diatomic. And so what we have to remember when they say oxygen gas, that we're working with O2 because it's diatomic. So once I identify the chemicals that I'm working with and or the formula I'm working with, a compound, I write the formula. From that, I then write down on the side the molar mass. Well, each oxygen is 16, so there's 32 grams per mole, okay? And I do that in the beginnings because I want to start off with a systematic approach of attacking these problems and gathering all the information that I know so I can help me down the road here to maybe I may use it, the molar mass, I may not, depends on the question. But if I do, I'm ready. I got it ready to roll there. Okay. All right. So they're asking you how many grams. So that tells you already you're looking for grams. How many grams is 1.667 moles of oxygen? So they want you to get to grams of oxygen. Then we write down what we're given. We're given 1.667 moles of oxygen. Obviously, we're going to have a conversion factor here. I'm going to have a conversion factor with moles in the denominator and grams in the numerator. And we're talking about oxygen. So it's understood that we're talking about oxygen here. So our moles of oxygen cancel out. So I got the units set up properly. Now it's a matter of putting in the correct number. And grams per mole, that's molar mass. So in this example, yes, I'm using molar mass and specifically 32 grams per 1 mole. Okay. And now I go ahead and I plug it in the calculator. Okay. Let me clear this so we can see what they did. And there we go. So 1.667 moles of oxygen weighs 53.34 grams. Okay. Now, with respect to sig figs, we're still going to use sig figs here. That doesn't ever go away. Remember, I told you way back when, always sig figs when it comes to scientific calculations. I stated that from atomic weight, molar mass, we don't use those to determine whether they're to determine the number of sig figs in our final answer, because these guys are averages of whole numbers and they have infinite number of sig figs, so we don't use them. But this number here, this mole, is a measurement. Okay, start off with grams and convert that to moles. So it is a measurement. So that, yes, plays a role in determining the correct number of sig figs. A note about atomic weights and molar masses. Utilize the atomic weights that are given in our periodic table. Yes, I know you can Google them and you Google the atomic weights. Occasionally, there's some variance, a little bit of variance with respect to the atomic weights, depending on your source. And so to keep matters consistent, our answers that we put into Canvas are based on the atomic weights of the periodic table that we give you. So use the atomic weights from our periodic table. If you use alternative atomic weights, sometimes they have more digits, more decimal places. Your number may not be correct as per Canvas, because Canvas's numbers are based on the sig figs of the atomic periodic table that we hand out. Okay. All right. We'll just use our periodic table, and that way keep things simple. All right. So 1.667 moles of oxygen gas weighs 53.34 grams. But that also tells you, interpret that the opposite direction, is that if I were to measure out 53.34 grams of oxygen, I have 1.1667 moles of oxygen, which is a little bit over 1.5 times the Avogadro's number. Okay, because I can calculate how many molecules that consists of. So we can do that. Let's do that real quick. 1.67 moles of oxygen. We want to know how many molecules that consist of. well, it's already in moles. All we need is Avogadro's number, 6.02 times 10 to the 23rd molecules for 1 mole. Okay, and let me calculate that and see what, let's see what, the 1.667, 1.667 times 6.02 exponent 23. And that gives me 1.00 times 10 to the 24 molecules. And so that would be 1.003 times 10 to the 24 molecules of oxygen, which weighs 53.34 grams, which consists of 1.667 moles of oxygen. Okay. Another way of saying that is 1.67 moles of O2 equals 53.34 grams of O2, which is equal to 1.003 times 10 to the 24 molecules of O2. Okay. Any questions about that? Now we're going to utilize the mole all the time. The mole is important here in these calculations because when we start dealing with reactions, okay, A plus B to give us C plus D. You know, if I start off with 10 grams of this and I want to figure out, all right, how many grams of D I make, I cannot go directly, okay? I have to go through moles. I need to convert my grams of A to moles of A, and then from moles of A, I get to moles of D, which then get me 2 grams. So our common factor is moles. So we need to really understand that concept. Okay, this one here, we'll break it down again. They're asking you how many moles is 45 grams of silver. All right, so we write down what we're given, 45 grams of silver. Okay, obviously I'm going to need the atomic mass of silver, and that will give me the moles of silver. And so that means that I need grams here and moles in the numerator, grams in the denominator and moles in the numerator. And so it's just silver, so we just need the atomic mass of silver, which is 107.87 grams. Notice that our grams cancel, leaving us with moles in the numerator, which is what we want. Okay. And so when you're doing calculations, and you're looking at reactions, you want to create a reaction to make a product. You determine how many moles of what you're working with is how many moles you need. And from that, you convert that to grams. Right now, we went from grams to moles, but you can easily go from moles to grams, okay? And that we're going to do that on in both directions, you know, just like the formulas. Given the name, write the formula, given the formula, give the name, back and forth. Same things here. We could go from grams to moles and moles to grams. Okay, now, we got water, and we did this one earlier. We need the molar mass of water. We came up with 18.02 grams per mole. Okay. And we want to know if we have 0.055 moles of water, well, how many grams is that made up of? So we write down what we're given, 0.0554 moles of H2O. Okay, I'm going to have a conversion factor here because I want to get to grams of H2O. And so we got moles of H2O, moles in the denominator, grams in the numerator. Okay, so that's 1, and that's 18.02 grams. Okay, check my units, always checking my units, make sure I set that up properly. And then I just simply do the math, and I should end up with almost 1 gram. So 0.998 grams of water is equal to 0.055 moles of water. Okay. Small quantity of water, but we can calculate the number of molecules, and it's still be a lot of water. Okay, because you know, if 1 mole weighs 18 grams, and we're like 1/18 of a mole, right? 1/18 of a mole, because 18 grams is 1 mole, and we calculated 0.9 grams per 0.05. So it's a small number, but the 0.05, but the molecules is still fairly hefty number of molecules. All right, now a little extra step. All right, we're asking for grams of potassium. How many grams is 4.75 times 10 to the 16 atoms of potassium? All right, we're gonna need the molar mass, and let me see, 39 points. Sorry about that. It was 39.10 grams per mole. Okay. All right, now, so we're given the number of atoms, 4.75 times 10 to the 16 atoms of potassium. So obviously we need a conversion factor here. And we eventually have to get all the way to grams of potassium. Okay. And so guess what? It's going to require 2 conversion factors. The first one is Avogadro's number, because Avogadro number relates atoms with moles. Okay. And so we want atoms in the denominator. So 6.02 times 10 to the 23rd atoms of potassium per 1 mole of potassium. And so if we stop the calculation here, we would just have moles of potassium, which is not what we're looking for. We're looking for grams. And so I need one more step. We're looking for grams. That means that grams in the numerator and moles is in the denominator. And that is essentially just basically the atomic mass. Okay. And our moles cancel to give us the units grams. So I set it up properly. Notice again here, I cannot go directly from atoms to grams. And the only way I can get to it direct, it had to go through indirect method. I have to go through moles. Notice our common unit is moles. I relate moles over Avogadro's number, and the weight or the mass over moles. That is our common unit, our common factor between the elements and reactants and so forth. So now I can simply do the math. And my answer is 3.09 times 10 to the negative grams. Again, it gives you a perspective as to the differences here with respect to the number of atoms and the weight. This 4.75 times 10 to the 16 atoms of potassium, that's a large number. Now, obviously not quite as large as Avogadro's number, and it's still pretty hefty. Okay, well, oh, I see 10 to the 16. That is almost, it's quintillion right here. 10 to the 18th almost, it's between quadrillion and quintillion with respect to value. So it's still a hefty number, okay, of atoms. But the weight for that large number of atoms is extremely small, 10 to the -6. Most modern balance, most balances you find, average balances in the product and the labs, cannot measure that accurately. Okay, you can go like our lab would have gone maybe 4 decimal places, 10 to the -4 maybe, and that's still iffy. And so there's the potassium, very small weight, has a very large number of atoms. Again, to give you a perspective as to the size of these atoms. There's a lot, they're very, very tiny. All right. Okay. Any questions before I begin? In fact, I want to try to keep you in line with the other section. They ended up a little bit earlier. We stopped at 9. You're like 1 page ahead, 1 slide ahead. And if you don't mind, I like to do, kind of stay within 1 or 2 slides between the 2 groups, because sometimes some people from here go to my 1 o'clock and vice versa. And then I got people at SCC to also join. So I try to keep everybody about the same slide, or between 1 or 2 slides of each other. So what I'm going to do is just stop it here. And we will continue next week. Let me do this. This is 12. You will stop at 10. Okay. And maybe we'll